Hi, I'm Tim Donaldson. I'm coming to you from Boston, Massachusetts today. And joining me on this case study review is Phil Arnold with Wright Pierce. Phil, I'll let you introduce yourself and talk a little bit about Wright Pierce.
Thank you very much, Tim. Wright Pierce is primarily a full service engineering firm based out of New England. I'm actually in the Portland, Maine office. We have offices in New Hampshire, Massachusetts, out in New York, and we also have a couple offices down in Florida. Primarily, Wright Pierce does water and wastewater infrastructure engineering. Relatively recently, we also started a full service integration group as well. So we have folks that go out and do PLC programming and SCADA development, and I'm actually part of the integration group.
What we're going to talk about today is an application that you actually built recently, and that was for the town of Exeter, New Hampshire, on their wastewater treatment facility. Can you just tell us a little bit about the wastewater treatment plant at Exeter and what some of the goals were with putting VTScada in?
This was actually a pretty unique opportunity on many parts, Tim. This treatment plant started out as a four lagoon plant with very little process control, with basically letting nature do the work. They actually ended up having to go to a full treatment process, of which Wright Pierce did the engineering, and we also did the integration and PLC programming, as well as the SCADA development. So the folks in Exeter went from managing some lagoons to managing a full-blown wastewater treatment plant with influent, headworks, sludge dewatering, aeration, and a UV disinfection system.
What type of PLCs and RTUs are used at this plant?
And this is primarily a Allen Bradley control logic based PLC control system. There's a couple of other PLCs out there. There's one Modicon. I believe that's it. Yeah, it's primarily Allen Bradley though.
Sure. Is it all one location where the data is coming from, or is it multiple locations throughout the town or throughout the plant?
Primarily, this is all on a local network, so it's all from the treatment plant, but they do have 9 satellite sites. So those are all remote pump stations, which we also did incorporate into this application. We're getting data from those remote sites through a Ethernet radio telemetry system.
What was some of the features of VTScada that attracted Wright Pierce to use VTScada for this project, or even or Exeter to buy in on that?
One of the big features that the folks in Exeter did like was the fact that it was a one-stop shop for pretty much everything that they needed. The historian, the alarm call out, also the redundancy as well, is all built right into the software.
And you mentioned a big part of it was being able to use high performance graphics and custom widgets and so forth for that. So maybe could you tell us a little bit about that, and then maybe share your screen, and if you can show us some of that application, that'd be great.
Absolutely. So right up from the beginning, we presented the concept of this high performance graphics, which is ISA 101 high performance HMI. Essentially, what high performance graphics is a way to take the data that we have in our controllers and our PLCs and our process control system and provide that in a more meaningful way to the operators, to let operators judge very quickly, is there a problem that I have to deal with, or is this system okay? Is this component okay? And really get to the root of, I need to give the attention to here, and I can ignore this over here because this is okay. And a lot of it is using visual cues, using symbology, to some extent color. And we're really not so much relying on numerical values to determine if the system is okay, but we're relying on putting those numerical values in context in relation to something else. Process ranges. What's an acceptable range? What's an alarm range? So here is our process overview screen for the entire treatment plant. Like I said, it's not a typical process overview screen. A lot of times you'll see a process flow diagram type screen that shows the entire process and some key values within that process. This screen is really more intended to show the general health of the system. And you can see we've embedded quite a few trends. Trends are very helpful in terms of judging what's going on because they show potential cycling, like we can see here. Here's a cycle. They show the history of what's happening, and you can actually use that to judge what potentially could happen in the next 10 minutes based on what's happening in the past. Without these trends in here, you would never know that this up here was happening. And that looks like a pretty wild shift, right? This is all influent flow. We had an effluent flow that went outside of the range of what we're saying is well outside of the acceptable range. So you could actually use this as a means to dive in a little bit deeper to this system and see what was going on. Another thing I was mentioning is putting this data in context. Right down here, what we have is, again, we have the numerical value, but we also have this little arrow and this gray bar that's showing the current value, but we have some other information around it showing the blue bar that's within an acceptable range. And then outside of the white bars, those are our alarm limits. So you can quickly look at this and say, hey, I'm right in the middle of the blue bar. I must be doing pretty well with that process.
That's great.
Another thing that we used is we're trying to combine several means of conveying information. And I'm going to point to these little pump icons. We have a check mark and a yellow X. Check mark means no problems here. Yellow X means, hey, there's something that's going on with this piece of equipment. We tried to make the check mark blend into the background and bring the warning conditions up to the front. So when you would be looking at this screen, maybe at a glance, you see a bunch of yellow X's, you can say, there's some problems here. I got to go and dig down what's going on. The white check blends back into the background because we don't want to bring a good condition to your attention. We want to bring the warning conditions to your attention. Another thing we are using is we're using color to convey several things. Green is running, gray is stopped, but we're also using text as another indication, because some people might want to look at colors and some people might want to read a text. And so we're making it adaptable for different operators.
As well as the symbols too. So you're using symbols,
Correct.
colors, as well as
Yep.
text. Nice, simple, clean design, Phil.
Thank you.
Tell us a little bit about how you created some of these custom widgets, and then show us that within the Idea Studio.
There's actually two components to this. One is building the tag database, and the other is actually developing the widgets to work with the tags that we built. And we actually heavily relied on the ability to create custom tag data types within VTScada. But the real power is we also have the ability to create those same data structures within the PLC programming. What we have been able to do is create a data structure in VTScada, create a data structure in the PLC, and then through the power of using expressions, linking through the parent-child relationship of the tag database, linking common tag names through expressions that actually directly address the PLC I/O. So for one example, we have a tag type that we call motor, and that has 81 descendants in it, 81 tags. And by linking by a single tag name by the parent, what we have is the ability to grab 81 data points with a single tag name. And what that does is that obviously streamlines database development, eliminates errors because we have the template that we already know works that's going down to the PLC and grabbing the right information, makes commissioning very, very easy. So here's an example of a motor that we also have. We have other children inside of this. So we're getting all of this information in here by a simple tag name, RSLP1. As long as we have that same data structure and that same tag in the PLC, we get all this data all in one fell swoop. The other thing that we've done in here is we've added some parameters to help configure this tag. So we can give it a name, and we can actually enable and disable different children in here based on whether this piece of equipment has, say, like a seal leak. This piece of equipment does not have a seal leak alarm, so we put a 0 in this parameter, and that disables all I/O associated with a seal leak. It's great for not using up your I/O tag count, because as soon as we disable this, that removes that from the tags that are used for the ones that you pay for. So we have several ways to configure this, several places to configure this, because every motor is not the same. So we get to say what is the max amps, and then this feeds back down into several parameters within the motor. So it's really truly a kind of a plug and play.
Can we take a quick look at the Idea Studio and some of those widgets that you built?
Sure. So now that we have these custom types, we also have widgets that work with these custom types. In this left-hand side, you can see the collection of widgets that we've developed. For instance, This widget right here is actually linked to one of our custom types. We call it a motor type. So everything that goes inside of this widget gets addressed at the top level of that tag. So all we have to do is say, I showed the example of RSLP1. All we do is we link this widget to RSLP1 and we get everything associated with this widget by one tag name. And actually I can show an example of that. There it is right there. RSLP1 gives you all of that information, including the actual name of the piece of equipment. So I don't even have to rename this piece of equipment. It all comes in with the tag.
From what I remember, that you started this project with version 11, and then you migrated the project up to version 12.
Yes, that migration went very, very smoothly. It was a matter of a couple of hours to update 2 redundant servers. We were actually able to maintain connectivity the entire time, at least with one server while doing the upgrade.
Let's talk about the redundancy for a second. As we know that we could physically have the primary in one building and the secondary in another building.
It's absolutely, as long as you're on the same network, you can locate them in separate buildings, and it's obvious. It is a safety factor because if you've got an issue in one building, you're still safe on the other side.
I believe you're doing something similar to that at Exeter Water, where this is the wastewater treatment plant we've been seeing. But can you talk a little bit about how you've implemented that at the water side?
Yeah, this one's actually really, really cool because what they have at the water site, they've got 2 independent water treatment plants that are physically separated by a distance of miles. And what we have at these sites are redundant VTScada systems local to each plant, but the plant is actually connected over the town's network. We actually have full visibility with a single application, full visibility of either plant from either plant, and they're all backing each other up. And if we sever the link between the 2 water treatment plants, each water treatment plant has visibility of its own equipment. You don't get to see what's going on at the other plant until that link comes back up. But as soon as it does, all of the historical data that both sites were collecting sync, the alarm history syncs, it all comes back together.
Well, Phil, I'd like to thank you for your time today. This has been a great insight to what's happening at Exeter.
Well, thank you very much, Tim. I appreciate the opportunity to show off some of the stuff that we've done with VTScada.